All right, everybody. So today we're going to be exploring balanced and unbalanced forces. Essentially, what is motion and why does it happen? So, balanced and unbalanced forces, definition wise, can be described balanced as motion that does not change, where unbalanced changes the motion of an object. For example, looking at this picture here. If you're waiting in line at the grocery store, still stationary, okay, no movement at all, you're balanced, right? Your motion isn't changing. However, unbalanced, you have to push and apply force to that cart to move up one step closer. And that's when your motion changes. You become unbalanced. And then what we're going to be seeing are these diagrams called free body diagrams that represent if an object is in balanced or unbalanced motion at that time. All right, so more free body diagrams. So how could we determine if these diagrams show balanced forces? What we would look for is we would look for the same amount of force on all vectors of that object. What a vector is these arrows that you're looking at, and they represent the forces acting on that object. The N stands for Newton, and that's the unit of force. And so looking at this example here, this is a balanced force because each force acting on this object is the same. What we do is we then subtract them from one another to get zero. Whenever you get zero, something called the net force, that also lets you know that a force is balanced. Okay. And so which show unbalanced forces, that would be all the other ones, because even this one here, I subtract 25 and 25 for 0, but I still have a vector acting on this side, so I have 20 newtons. When you see the vector, it's not necessarily this side is where the force is coming from, but it's where that object is moving. So this object is moving to the right, this way, if you're looking at it. Looking at these ones, there can be more than two forces acting on an object, more than three for sure. Looking at this one, if you subtract the opposite vectors, you would also get 0. This represents a balanced force as well. This one here, we have 0 as our net force. However, we have two different values here. We would have 5 newtons left over to this direction. So these two diagrams here represent objects that are moving in this direction. However, balanced forces can still be in motion. For example, this could represent a car that is going the speed limit. It's going the same speed for the same amount of time, all right? And so this can also represent a balanced force. Remember, because it's motion that's not changing. So if it's a continuous motion, it's also balanced. Okay, so why don't you pause for a second just to think about this free body diagram. What would you do to find the net force, and which direction is the skier moving? Okay, hopefully you've unpaused at this point. And so if you look here, these two forces are the same. And we saw that in the previous examples as well. Because objects that are on surfaces on Earth have this force acting on them called the normal force. And so it counteracts gravity pulling down. This is why you're not floating up into the air, or opposite, why you're not crashing into the ground. The normal force and gravity are equal to keep you and all other objects on Earth in place. Now, looking at these two opposite vectors, we see 410 newtons and we see 300 newtons. If we subtract those two, we would get 90. Woo! No, we would not. We would get 110. Sorry. We would get 110. And so what this tells us is that this skier is moving this direction with that many newtons. And this represents here, all right, the pull of the skier down and its influence, by his skis, the surface that he's on. And then also resistance, friction can help, keep something back, all right? It keeps him in a little bit of control. Now, we can use Newton's 3 laws of motion to describe unbalanced and balanced forces as well. So here are Newton's 3 laws defined. His first law of inertia states that any object will remain at rest or continue to move uniformly, or in the same way, in a straight line at a constant velocity, speed, and direction, unless acted upon by another force. So for example, something is still on your desk, you push it, that's inertia. You can also remember the Newton's cradle I have in the classroom? It'll stay the way it is until you decide to move it. His second law is something as we refer to as F equals ma. And it's the rate of change of velocity of an object is proportional to the force acting on it. Another way to think about it is that the mass of an object determines how much force is necessary to move it. For example, this guy is having a really easy time accelerating this lighter ball than this guy who's trying to push this 400-kilogram ball. If they use the same amount of force, this one will be much harder to push. Last one, the most common one that comes to mind, is action-reaction, or essentially one object exerts force on another, and that second object exerts an equal and opposite force on the first. Or in other words, every action has an equal and opposite reaction. That's why rockets propel into space. The fire from the exhaust shoots down and propels the rocket upwards into space. You can use Newton's laws in bowling in all different ways, and a lot of the times they happen in tandem or at the same time. For example, the bowling ball will knock the pins over, all right? The pins will stay there unless acted on by another force otherwise. And so you can use that inertia, his first law, to describe this phenomena here. When you're bowling, it's definitely a little strategic when you first start. Which ball are you going to use? I know whenever I go bowling, I figure out, okay, what's going to be the right amount of mass for me to knock the most pins over, but to also keep it in control and be able to lift it up. And so that's where his second law applies in bowling, because different amounts of forces will be required to roll different masses of the bowling balls. Now, action-reaction you can see here, okay? When you walk forward towards that bowling alley, all right, you're pushing actually back on the wood to move you forward, action-reaction. And then when you think about swinging that ball, when you bring your arm back, that opposite reaction is going to then propel your arm forward. So pause for a second here to think about how you could use Newton's laws, the information, to interpret data and to interpret a diagram to figure out how Newton's laws are causing these objects to move. Okay, so hopefully you've unpaused, and let's look at this question first. So it says a student is performing an investigation. She applies the same amount of force, so that's key, same amount of force to the soccer ball and volleyball, and observes their acceleration. And so we see here on this table that the objects have different mass, all right? With the same force applied, they accelerate at different rates. And it looks like this one has a higher acceleration. which makes sense because according to Newton's second law, F equals ma, if there is less mass with the same amount of force, it will accelerate more. And so if we were to look at our choices here, we would want to look for a combination of acceleration increasing because the mass is different, okay? And so let's take a look at our choices here. And it says, oh, sorry, let me actually go back and read the question. I am not modeling best practices. Here we go. The student claims that a bowling ball, all right, so they're going to add something into the mix, a bowling ball with a mass of 5.5 kilograms. So let's see where that fits on our chart. That would be heavier than the two here. That student claims that a bowling ball with a mass will accelerate faster than the volleyball and soccer ball. Okay, so if we have a heavier mass with the same force, we're definitely not going to see that, all right? It's going to require more force to go faster, so that student actually is incorrect. So let's go down to C and D. And so our best choice here would definitely be C because acceleration is going to decrease as the mass of the object goes up or increases. And so what I did, which you definitely shouldn't do, and I'm actually kind of glad I did it because it's a reason why a lot of the times we get questions wrong. If you just go right from data to choices, you might miss out on some important information. So definitely look at all the pieces before you decide to pick your best choice. Okay, now let's look at this diagram over here. These are spring scales, and what they do is you can attach an object to this hook, and when you pull it, it'll tell you how many newtons of force are required to move that object on that surface that it's on. And so the student measures two blocks with different masses, so they don't have the same mass, with spring scales as shown, okay? And so if we look at these two spring scales, it's looking like this one has more force required to move it than this one. Because if you see, this one takes about 2 to 3 newtons, or this one takes about 5 to 6. And so we would definitely determine which one has a smaller mass by this information. And so let's take a look at the choices here. Okay, so what makes sense here, especially with this information here, is that block 1 is going to have a smaller mass than block 2. Now, because of that, block 1 is going to require less force to accelerate, again, due to Newton's second law. So B is our best choice here. And so that's kind of, how you can use these laws in the real world. When you see motion occur and experiencing it yourself, what about Newton's laws is allowing that motion to take